So we're going to begin to learn about the ideal gas law in its simplest form. Here we have the ideal gas law PV equals nRT. R can be represented with different numbers depending on the units that are used. The R that we're going to use for our a universal gas constant is 0.0821, rounded here to the nearest 10, rounded to the 10,000ths place, because we're using the units atmospheres, liters per mole, Kelvin. We know liters are units of volume, kelvins are units of temperature, atmospheres are units of pressure. So the first example problem we're going to look at, we can begin to read it. It says if 88 moles of hydrogen is stored in a 4-liter container at 304 Kelvin, what is the pressure in the container? So what are we given? We're given our 88 moles, 4 liters, 304 K. What are we looking for? We're looking for pressure. So we begin this problem, our strategy, by writing down the ideal gas law. Now we're looking for pressure, so we want to get the P by itself. To get P by itself, we have to divide both sides by what's next to P, which is V. Divide both sides by V. And we get P by itself. Now we can just simply substitute into the modified equation for the ideal gas law. And when we do that, we always want to put in all of our units. So 88 moles times the universal gas constant with its units times the 304K divided by the volume, which is 4 liters. Now, before we get a number, it's always good to check your units to make sure that your work is correct. So our moles cancel, our Kelvin cancel, our liters cancel, and we're left with atmospheres, which are in fact units of pressure. And you end up with 550 atmospheres. Why is it 550 instead of 549? Actually, this should be 500 atmospheres. And I'm going to explain why. It should be 500 atmospheres because in our problem, the number with the smallest number of significant digits is 4 liters. There's only one significant digit here. So 549, which is the answer, the numerical value you get when you do this math, would round down to 500 to one significant digit.